hope you're ready to learn about periodicity. I put this topic into inorganic chemistry because normally I teach it together with group 7 and group 2, but it's kind of physical chemistry. Anyway, I hope you enjoy it and you can join the full AS chemistry crash course by clicking the link in the description. If you have any questions, feel free to comment below because I'm here to help you. For a lot of free resources, check my website and enjoy learn. Hi there. Today I want to give you a bonus video. We talk about nuclear attraction, one of the most important concepts of chemistry. If you understand this, you will be able to apply it to the explanation of many different trends from ionization energy, trend in electronegativity, in lattice enthalpy, even strength of bonds, boiling point, melting point, and many others. Let's get started. Nuclear attraction is also called effective nuclear charge because it's the actual amount of positive charge experienced by electrons. Okay, and this can be electrons in the atom, can be electrons of another atom, can be electron in a bond. It depends on the charge of the nucleus, and this is called the nuclear charge, which is relative to the number of protons that are present, and the distance to the nucleus. The effective nuclear charge decreases with an increase in shielding, and this is the other very important keywords to understand relative to the distance to the nucleus. In fact, shielding is this effect, basically is the blocking of the valence shell electrons attraction by the nucleus, and this is due to the presence of inner shells. Okay, so the distance to the nucleus is affected, and the attraction to the nucleus is affected by the full shells that hinder the positive charge of this nucleus. So the effective nuclear charge decreases with an increase in shielding because the positive charge is, let's say, covered. It's decreased by those full shells of electrons. But of course, the nuclear charge increases with the effective nuclear charge, or the nuclear attraction, increases with an increase in nuclear charge. So the more protons are present, the higher the nuclear attraction. However, the higher the shielding, so the more shells are present, the lower the nuclear attraction. Yeah, and the shielding always outweighs the nuclear charge. So, for example, sodium ion has a higher effective nuclear charge or nuclear attraction than potassium ion because sodium has a lower shielding. Calcium has a higher nuclear attraction compared to potassium because it has a greater nuclear charge, but same shielding because they have the same number of shells. Okay, don't worry, I will repeat this other times when we explain in more details other trends. So the nuclear attraction is very important because it affects all of the properties that involve any type of electrostatic attraction: ionization energy, atomic radius, electronegativity, affinity, bond strength, oxidizing, reducing ability. So many. Always think it as whenever there is an electrostatic attraction. Okay. Let's look at the trends, and then maybe I will explain some of this more specifically. So the trend increases as we go across the period because as the nuclear charge increases, the shielding stays the same as we go across the period. Yeah, because remember that the period is it represents the number of energy levels. So if the elements are in the same period, they have the same number of energy levels, which means that the electrons are added onto the same energy levels. So it doesn't increase in shielding. So increase in nuclear charge because there are more protons, but the shielding stays the same because the electrons are added to the same orbital. While the nuclear attraction decreases as we go down the group. The reason is that there are more inner shells, and this is the shielding. So as we go down the group, the shielding increases. Okay, and those are the keywords to use. In fact, look at this exam style question that it's about the attraction between particles. State how and explain why the attraction between nuclei and outermost electrons in gaseous atom varies across period 3. Okay, so the way to explain it is the attraction, we can call it nuclear attraction, it would increases or the nuclear charge increases, or the number of protons increases. Why? Because the electrons are in the same shells, and the number of protons increases. Those are the two key things. Either same shielding, higher nuclear charge, or you can explain it actually in terms of structure. Okay, so I hope this is clear, and let me give you one explanation of the trend. So here we talked about the ions. So sodium, potassium, it was a difference in shielding, because sodium is a smaller atom because it has less full shells, and the difference in charge. But if we don't have an actual charge, for example, in this diagram where we have two covalent bonds, well, the nuclear attraction is what determines the bond strength, because do you remember the covalent bond is an electrostatic attraction between a positive nuclei and the shared pair of electrons. There we go. It's all about nuclear attraction. So the stronger the nuclear attraction, the stronger the bond. For example, fluorine, it's a smaller atom, it has less shielding, so the nucleus will be more attracted to the shared pair of electrons. Chlorine, more shielding, so there will be a weaker attraction. Okay, so what you can do is think about the definition of all the trends of electrostatic nature that you've studied so far, like electronegativity, ionization energy. If in year 13 you can include polarizing power, oxidizing, reducing ability, enthalpies, and try to explain it in terms of nuclear attraction. You will see that pretty much all the trends, they're explained in the same way. So the takeaway point from this lesson is that nuclear attraction is really one of the most important concepts in chemistry, because it helps you understanding the reason of many other trends. So stay tuned, because now you can apply this concept of nuclear attraction to understand the periodicity topic. Hi, and welcome to this lesson about periodicity. Today we describe ionization energy and trends across the period 3. Let's get started straight away. One little thing before we start. So we will link the concepts of electronic configuration to explain some of the trends of ionization energy. So it's important that you remember how to write the electronic configuration, as well as the rules for filling orbitals in energy diagrams. And very important, the concept of nuclear attraction, because this will explain a lot of these trends. So if you haven't watched it yet, go and look at the extra video of nuclear attraction before you get started. Otherwise, let's skip this bonus lesson that I've already given you, and let's go straight into ionization energy. So the first ionization energy can be described as, let me just get the little laser here so you can follow me better. So the first ionization energy of an element is the energy needed to remove 1 mole of electron from each atom in the gaseous state to form 1 mole of gaseous 1 plus ion. Could be complex definition, but remember that our values are energies that need to be compared, which means that all of the elements, they have to be in the same state. That's why they're gases, and that's fundamental for you to write it in the equation. And then it's an energy, so you can always start the definition as energy required at 2. Does that remind you of enthalpy? Yeah, same. So first ionization energy is to form 1 plus ion. Okay, because remember that ionization energies, they are successive. So what it means is that 1 electron at the time is removed. So there is a trend of successive ionization energy. Those increase. Okay, think about why. Because as the electrons are removed, the nuclear attraction to the remaining ones increase. Therefore, more energy is required to remove them. And if we want to write the second ionization energy, we would always start with a 1 plus ion to form 2 plus ion, and so on. So let's look at the trend in the periodic table. As we go down the group, the ionization energy decreases, and this is because the shielding increases. As a consequence, the nuclear attraction decreases, which means that it's easier to remove the outer electrons. An alternative explanation that, without mentioning shielding and nuclear attraction, is just saying that, as we can see from this diagram, as we go down the group, the atomic radius increases. Okay, which means that the less energy is required to remove the outer electrons, so ionization energy decreases. Okay, so find a way that you're comfortable in describing this in terms of atomic radius or shielding and nuclear attraction. Both will be accepted in exam questions for, from the marking scheme. So down the group decreases. Across the period, it would increase. Okay, let's think about why. So across the period, the nuclear charge increases, but the shielding stays the same. Okay, because electrons, remember, that are added to the same outer shell. Okay, which means that they are at the same distance from the nucleus, but there are more protons and more electrons, so there is a stronger attraction. So overall, these electrons will be closer to the nucleus. Okay, which means that as we go across the period, the general trend is that the ionization energy increases. But there are some exceptions, and let's look here. So it's common for all the groups, but here let's focus on elements of period 3. Sorry, it's common for all periods, but let's look at period 3 elements. There are some exceptions, so notice that the general trend increases. However, there is always an exception from group 2 to group 3 and from group 5 to group 6. From group 2 to group 3 is because the full SO2 orbital provides extra shielding, and this makes the P1 electron easier to remove. Okay, because the 1s orbital or the 2s orbital provides extra shielding. Okay, so the P1 electron, like in this case of aluminum, it's group 3, it's P1. In this case, they would be, the electrons are a little bit further away from the nucleus, so will be easier to remove. Between group 5 and group 6, there is one electron, as you can see, paired up. So the P4 electron is paired. Therefore, the extra repulsion would make it easier to remove. So the strands are common for group 2, group 3 of all periods, and group 5 and group 6 of all period, because of the arrangement of the electrons in the energy or in the energy levels. I hope this makes sense. Let's look at an example. Do you want to try to work it out for a moment? And then I will walk you through, but this is a typical exam question, multiple choice or even open question. So read it and then I'll walk you through it. So think about what we said in terms of trends. Okay, there is one that I haven't mentioned, but I would like to mention it using this example. So element X is in period 2 and has the first 7 ionization energies written here. So as we said, the ionization energies increase. Yeah, the successive ionization energy increase. But also notice that this is the lowest energy, which means that is the electron that is the further out, right? So it's the kind of 7th electron, even though it's the first ionization energy. So notice how there is increase, 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 huge increase. There is a very big increase from the 6th and 7th ionization energy. Think about what that means. So we know that the increase is successive because there are less electrons remaining, so there is a greater nuclear attraction to the remaining electrons. But when there is a huge gap between ionization energies, is because we have entered a new shell closer to the nucleus. Okay, so if we break up into a new energy level that is closer to the nucleus, there is a big difference in ionization energy. And this tells us that we had to remove 6 electrons before going into the 7th. So this tells us that the element has 6 electrons in the outer shell. So this can help us working out the group number. So this will be in group 6. So if it's also in period 2, we know that it has only 2 energy levels, so 1 and 2, so 1s and 2. And if it's in group 6, it would have 6 electrons in the second shell. Therefore, this is the correct option. I hope this makes sense. And if you're ready to move on, let's do it. Otherwise, make a note of the questions you have and let me know after the lesson. So let's talk about periodicity. and it's still about trends in the periodic table. And I've included the explanation together with the ionization energy because at the end is all down to this explanation of nuclear attraction. So, as a definition, periodicity is the recurrence of the same pattern across the periodic table. And there are different trends that you need to be able to describe. One of them is the atomic radius, or atomic radii, if you want the plural. So if you think about it, we go across the period. What trend did we say is the most important? The nuclear attraction. So as the nuclear charge increases, but the shielding is the same, the outer electrons are more attracted to the nucleus, which means that the atom will decrease in size. Okay, they will shrink because of the greater attraction. Okay. Second trend to know, melting point. This is comes from your knowledge of bonding, so will be a nice revision. So always focusing on period 2, but period 3 would have exactly the same trends. Sorry, period 3, but group period, all the other periods would have the same trends. Sodium, magnesium, and aluminium, they have metallic bonding. So first of all, we know that they have very high melting point because that they have because they're giant structures. But think about the trends within them. If you remember the discussion about boiling points, we said that that there are some factors, common factors that affect the strength of the bond. We're talking about metallic, which is electrostatic attraction between the positive metal ion and the localized electrons, which means that if there is a greater charge and there are more electrons, there's going to be a stronger bond. So more energy is required to break it, therefore higher melting point. In fact, from sodium to aluminium, it increases, even though magnesium and aluminium, they're quite similar, but it increases. Silicon has a giant covalent lattice, so this is really one of the strongest ones. Yeah, in fact, notice that there is a spike in boiling point. Then, after silicon, so after group 4, we have simple covalent molecules. For this period, it's important that you remember that phosphorus exists as a P4, sulfur as 8, chlorine as a diatomic molecule, and argon as an atom because it doesn't form covalent bonds. Okay, and if there are simple covalent molecules, we needed to compare the intermolecular forces. They are elements, which means that they don't have difference in electronegativity, which means that the only force that is relevant in the is the van der Waals or London dispersion force. Depends on the number of electrons. So as 8, because it has 8 electrons, it's the strongest. So notice that there is an increase from phosphorus to sulfur, but then there is a decrease of chlorine to argon because they are smaller molecules. Okay. So as you can see, this is applying the concept of melting point, of bond strength and different type of structures to different trends. Okay, and we're already at the end of the lesson. Please practice. So find your own way to explain this concept of nuclear attraction, and check the solutions, and make sure that you're confident with all the points. Okay. If you have any questions, let me know.